proportions. The first one, sample sizes, I think it's actually pretty straightforward because what you end up doing is you just remember one formula, this one, and solve for n. So multiply across. Divide by the margin of error, and that margin of error can be whatever you want it to be. Literally, you quite often decide what margin of error you want. And since you clearly don't want the square root of n for a final solution, you square like so. And that's what you have down here. Now, one thing, when you find an n, of course, it's going to be a whole number, right? In general, when you actually have a sample, you're not going to have partial observations. But let's say that you come up with an e, or some margin of error, that is half of what you had before. Well, there's no guarantee that the new margin, well, actually, if it's half, you will get a new integer, but if you decide on some arbitrary margin of error, there's no guarantee that your solution for n is going to be an integer. In which case, you always round up, because if you fail to round up, and you've specified a maximum margin of error you're willing to live with, then you can, in fact, violate that maximum and end up with a margin of error that's slightly larger. So, you see that, because if you decide that you want your margin of error to be no larger than some quantity like this, then you can follow the inequality through like so. Oh, wait. Backwards. Let's see. So, right. So this is your maximum margin of error you're willing to live with, and so you want this to be the case. And when you multiply across, then all right. 0 for 2. Right, no, you do want it this way. This is your maximum margin of error. So you want this piece, the calculated margin of error, to be no larger than that piece. In which case, you're going to get that n is going to be greater than or equal to this thing. So if this is non-integer, then you round up. Even if it's a small, non-integer piece. And that bottom part there is just the same thing, but what I recommend is remember the method, because that way you can just remember two different margins of error, one for means and one for proportions. Otherwise, you're going to be remembering 6? Oh no, at least 4, and for no particular purpose. You'll notice, though, that even when we're dealing with any type of mean and we're calculating the sample size, we have z here. And there's a reason for that. Any guesses? If the sample size was small enough, you couldn't use z, you would have to use, what did we just discuss? T, right? But the problem with that is, okay, here you can just solve for n. If you have a very small sample size, or small sample size, what ends up happening is that you'd solve for n, right? N minus 1 would be a new t, then you'd solve for another n, and a new t, and another n, so you'd basically be going around and around this, iterating for a while. And that's why, typically, you assume that your sample size is going to be at least 30, use z, you get an answer. And the reason is that it's just t to do so otherwise. Okay, so using the example with the income, 21,100 income and the $4,500 standard deviation, instead of a margin of error, which was $1,470, we want to force the margin of error to be no more than $500. How do we do it? Well, we insert $500 there, confidence level there, which was 95%. S was 4,500, and and that allows us to solve for n. We get a sample size of 311.17. 0.17. You do not round down, you always round up. So the sample size required is 312. Questions on that?
We're solving to find the sample size of what?
Right, because what often happens is that you'll do a preliminary study or a small study, and you'll get some answer, and it's not actionable, and you basically don't have enough precision to decide what you're going to do. Like, for instance, imagine that you're interested in the launching of some toy, and you're not really sure what people are willing to pay. Well, let's say people are willing to pay $12 versus $20, or even 12 versus $14. That might have a significant impact on how many you import. It can have an impact on what materials you use. It can have an impact on even the speed with which you deliver, if you get rebates as to lead time. But in order to estimate the amount people are willing to pay for a certain doll, you would have to have, you might need a very large sample size and more than you get in a pilot study. So you get a pilot study, the pilot study gives you some idea. It also gives you a way to guess at what the standard deviation is. And then you decide, okay, how large a sample size would we need in order to make an informed decision? And then you turn around and you gather the necessary data.
So what would you know the margin of error we want to achieve? So we have to find the sample size.
You would choose,
Oh,
right? Because in the real world, basically you're balancing. Precision is a good, cost is a bad. So you want to balance this out until you're roughly equal. Gathering more data would give you less benefit than the added cost. Alright, and the last subject is the exact same as what we talked about for means, except you now do it with proportions. However, it's so much simpler that we cover it all at once, together with the sample size. There's only one approach to doing proportions. We always use Z. We always use a standard error calculated using sample proportion here. Remember last time? We had the actual proportion, the mean proportion in the population. Well, we don't know that now, so we have to use the estimated proportion. Notice, however, that you're really only calculating one thing. You're calculating the proportion in the sample, and that gives you the entire confidence interval. Right? But the interpretation is the same, and you always use Z. One difference, though, is how do you know if you have a large enough sample? Remember that from last time? What is the magic number when you're dealing with proportions? 5. Excellent. And for confidence intervals, we're really looking at two groups. You just have to have at least 5 members in each group. And you might need some examples to think about there, but that's really all you need to do. In today's election situation, it's common to use polls as examples. Let's assume that we have a poll where 220 registered voters out of 500 favored a particular candidate. We want a 95% confidence interval. Well, we plug in 220 divided by 500 to get our sample proportion of 44%. 44% times minus 44 divided by 500 gives us, well, take square root of that, and you get your sample standard error. Multiply that by 1.96 because of what now? 95% confidence level, right? That gives us the margin of error of 4.35%. We add and subtract the margin of error from our sample proportion of 44%, and we find a confidence interval from 39.65% to 48.35%. Okay, anybody want to take a stab at the interpretation? Resounding silence. No? Well, actually, it's right here. We're 95% confident that the true population proportion lies between those two numbers, right? What is the probability that the true population proportion of registered voters that favor that candidate lies between those two numbers? 0 or 1. And now you're not falling for this one. It's actually not possible to formulate my third favorite question. Because how do you ask, what proportion of voters favor this candidate with between 39 and 48% of their psyches? And you can't really assume everybody has a split personality. So you just can't ask that question. It makes no sense. You can ask the probability that the sample proportion lies within your confidence interval. That's a trick question, which Steve knows the answer to.
That's false, right?
What's that?
Was that 0?
The one.
That was 1.
One, yes. Remember, every confidence interval is built around some test statistic or some sample statistic. In this case, P bar. We're building the confidence interval around P bar, so P bar will always be inside your confidence interval. So that's pretty much it in terms of interpretation. Oh, except for one thing. Can we conclude that a majority of the voters do not favor this candidate?
Yeah,
Because?
the maximum is for point 4835.
Very good.
It's less than 50%.
Exactly. The 0.5 is the key number. And here we have the entire confidence interval to the left or below, so we can conclude that at least a majority do not favor this candidate. It's not saying that they favor somebody else. It could be the most favored candidate that's available. But if you add together all those who favor another candidate or don't have any favorites, that is the majority. Okay.
How can we conclude that conclusively when we're doing the 95% confidence?
You can only conclude that we are 95% confident that a majority.
Okay.
Yeah. No, we can't say with probability 1.
Okay.
Exactly. Other questions, comments, prayers? Okay. So how do you calculate sample sizes? Ideal method. That's why I suggest you memorize the method rather than or just know the method. Again, we have a margin of error, and we want to make sure that z square root p bar 1 minus p bar over n is less than or equal to that. You multiply across by the square root of n, divide by m, and then, just as before, you square. So you need the p bar from your initial sample to estimate, but it turns out, and we can show this if you like, that if you plug in p of a half, you get the largest possible standard error, and therefore the largest possible margin of error, and therefore, as long as you are using p equal to 1/2 for planning purposes, you are conservative, because you will get the largest possible sample size needed to find that margin of error. It's a handy thing, and we can show this if you want to, but in the years I've taught this, I've only had one request to show it. But yeah, happy to do it. Let's change our example slightly and assume we want a 99% probability. So we're changing both the confidence level and the margin of error. Remember, the margin of error was 4.35%. We want it down to 3%. This could be CNN last week before the election, right? They want to know more. They want to be more comfortable with their predictions. So, what was the sample size? 500. Before there were 500 observations. Now we want to figure out what number of observations will drive our margin of error to 3% percentage points with a 99% confidence level. So just based on what we've already talked about, you can tell me something about what that sample size is going to be. More than
500.
500. All right. So we basically just plug in. Well, actually, it'll be on the next slide. We just plug in those values. 2.576 comes from the table, right? 99% confidence level. Our new margin of error, 3%. We use the proportion we found in our pilot study, and we get 16 point something, which we round up to 17 observations. If we had used a proportion of 1/2, in other words, with no pilot study whatsoever, we would have come up with 1,843 observations. And clearly, this is significantly more than what you needed for the previous study. It's nearly 4 times as many observations. So it's not something you do for no reason. But I have noticed that as you get closer to the election, you'll find that the polls reported have narrower margins of error, and that's not because they're less confident. I'm pretty sure they have larger sample sizes to base their estimates on. Any questions on that? Okay, so before we do the problems for this section, what you have to take away from today are the confidence intervals have certain correct ways and wrong ways to interpret what confidence itself means, right? You were confident in the method, and the confidence level tells you the probability of capturing the true mean before or true parameter, before you gather your sample. After you gather your sample, you can only say that you are 95% confident, or however confident you are that you did capture the sample, because the probability of doing so is 0 or 1, that the true population parameter is inside the confidence interval. You do need to know the role of the central limit theorem. The sample size needs to be 30 or more for a large sample hypothesis test, confidence interval for mean. You definitely need to know the assumption to make it possible to create a small sample confidence interval for mean. If you have a small sample and less than 30, what assumption do you need? What is some additional assumption?
Normal distribution.
Very good. The parent population must be normally distributed. Okay. And you will also need to be able to create and interpret confidence intervals for proportions, as well as find appropriate sample sizes. Okay. Let's do a few problems on that to nail down the issues. So problem 50, we have a preliminary study of mileage in an type of automobile. We want a 98% confidence level. Any intuition as to why you might be asked to use a 98% confidence level?
Other than you can never really get 100%.
Well, as opposed to using 90, 95, or 99%, which are sort of the standards.
Marketing.
It could be. My guess, though, is it's just that they want to the writers want to make sure that you can get practice reading the table. Make sure, once you can read the table, they're happy. Okay. The desired margin of error is 1 mile per gallon. The standard deviation we're going to use for planning purposes is 2.6 miles per gallon. And we need to find n. Well, remember, it's still here, right? So basically, we have 1 mile per gallon. We want to be the upper bound for the margin of error. We know z, actually we're going to find z, but we have s, 2.6, so we need to isolate n. So when we go through this series of steps, we're really only stuck with one single piece of unknown, or one part that's unknown, and that's what we get from this. way to do this is to recognize that the right-hand tail has to be 0.01, follow that all the way down, and you'll get a z of,
Point to one or point to two? Oh, yeah, so. Right.
oh, that's good. And what is z? Making sure we can read the table. Okay. Not quite that much. This is one of the non-standard ones, you have to look it up. What's that?
Should make, 15 degrees of freedom, so n equals 16.
I'm sorry?
15 degrees of freedom
Where do you get the 15 degrees of freedom?
off of the T distribution.
Well, why 15 degrees of freedom?
0.01, finding 2.6.
No, 2.6 is a standard deviation. I definitely don't want to use that. What you want to use is either the 0.01 in the tail, or this piece, which is how large?
That is
Half of 98%?
Yeah.
This is 49%? So you either look up 0.49 in the Z table, or you find the column headed 0.01 in the T table, and follow that all the way down. Remember, the Z is the T with infinite degree of freedom.
So it's, 1.282.
No, you're looking at 0.1, not 0.01.
0.6879.
How about 2.326?
2.327. Let's make sure that we're all on the same page here. I'm sensing a little bit of confusion. This would be my spider sense. Okay. Look at something. Look at a blank screen. It's all very exciting. Okay, so this is the T table. And of course, now it's there we go.
We are using T table because sound size less than.
We're using the T table because I'm lazy. Because it's easier, I'm just using the bottom row of the T, which is the same thing as the Z. Look over there. You see that 0.01, right? It's easier to find that 0.01 than it is to find 49% in the body of the Z. You just find that 0.01, you follow that all the way down, and you're done. Everybody see that?
If you had to choose the other way, how do you do it?
Okay, so the other way, do you see why this has to be, this piece is 0.49?
Yeah, half of it and 9 addition.
What's that?
Because 9 addition. and,
Right. If it was that 10th edition, you'd be looking at 0.99, right? Okay, so I can't read that. .49, where is that? Yeah, that's probably the closest you can get, 0.4901. Follow that all the way to the left, you get 2.3. Follow that up, you get 2.33, right? So the T table is actually a little more precise as well. Any questions on reading the table?
Okay, and the reason that we're using the last row, why are you
equal to Z.
using
The last row?
yeah,
Because it's the same thing as the z. The t with infinite degrees of freedom collapses into the z. It's the same thing. It's just easier to read that part of the table, I find, than actually digging through the z, 4.49. Okay, so, figuring out the sample size then reduces to plugging into the formula we just derived. So n is greater than or equal to 2.326 times 2.6 divided by 1 margin of error squared, and that's 36.7, which means that n is equal to what?
37.
37. Good. For some reason, usually on test 2, somebody decides that we should round down. That would be an unfortunate innovation. Questions on that? Okay. In that case, we need to look at proportion question. And in problem 54, we have that 369 working parents felt they worked too much, which gave us a point estimate of the proportion of the population of working parents who felt this of 0.542. We're also asked to find the margin of error and the confidence interval. So, in order to find the margin of error, we need that confidence level. But remember, the margin of error always uses z, so we don't really, I'm pretty sure we've memorized that by now. .96 square root 0.542, 1 minus 0.542 over 369. And that is a little more than 5%, which doesn't really have much of an interpretation standalone. You instead complete the job and find a confidence interval for the proportion of 0.4912 to 0.5928. Okay. And what is that interpretation? I'll give you a clue. We are. That's how you start.
95% confidence.
Excellent. We want to continue with the ball. We are 95% confident that the,
Population mean
not mean, but population
proportion.
proportion, yeah.
It feels they work too much.
What's that?
It feels that they work too much. Is
Yes.
between 49 and 59%.
Very good. Can we be can we conclude that we're 95% confident that a majority of working parents feel this way? this interval spans 50%, remember, you can think of this almost like a focal length. Every number inside your confidence interval, you can't tell apart from any of the others. So here, 50% is there, and your confidence interval looks like this. You can't conclude to a 95% level of confidence. So there are two ways we can go with this. We can answer that initial question, but let's answer a different question first. If we want to retain the level of confidence of 95%, but we want to be able to conclude, then choose some margin of error that will allow us to conclude. Okay, does everybody understand what I'm trying to get at here? I want to figure out how large a sample size we would need in order to draw some kind of conclusion. In other words, we want to pull that lower bound of the confidence interval above 50%.
Increase the sample size.
Yeah, right, and we want to find out how much we need to increase the sample size to.
So use the margin of error should be lower.
Exactly, and we're going to call that, we'll call that E, and pick one.
What was it called?
It was 5.08%.
We need it to be 4.2%.
Okay,
We need it to be 4.2%.
4.2%, sure. That would give us that would get us right at the border, right? So we'll use that for planning purposes, and we'll use everything else the same. Now, I just erased the part we need naturally. So, let's see, E, C, bar, minus bar, over N, we solve, we get that N is greater than or equal to, E, no we don't. Z over E squared, P bar, 1 minus P bar, which is 1.96 over 0.042, 0.542, 1 minus 0.542. That, I've got one piece. Square that. And that works really well. And then we want to multiply that by multiply that by 1 minus, which is 0.458. Oops. So n is equal to what? 5.1. So the minimum amount you would need, based on this structure, is 541 observations in order to conclude one way or the other. A very similar question is, what would happen if we calculated the same thing with 99% confidence? Well, okay, let's say we still want to keep the E at 4.2%, but we want 99% level of confidence now. What would change?
G would change.
Go to
Right.
2.576.
Exactly. So that's really the only thing that would change. And in that case, it's sorry? So we'll just call this N sub, well, let's call it 99%. Would then be greater than 2.576 over 0.042 squared, 0.542, 1 minus 0.542. Actually, we can do even better than that. Instead of using our planning position, let's assume that we don't know anything about the right proportion, in which case you have a P of 1/2 times, well, I'm sorry, let's do both of them. Just to compare notes. And in fact, if we didn't know anything about, if we hadn't done a pilot study, but we wanted to know, we wanted to have 99% confidence and a margin of error of 4.2, what would change? Just P, that's it, right? So in that case, you would get $940.4, which means that N is 941. So you see the difference is minuscule.
What was that last question, last scenario answer?
No pilot study. So you don't know what the proportion should be. And, you know, it's often a good idea just to try this because, you necessarily estimated the 0.542, so you might not be right with that one. Okay. So questions on, actually, anything we talked about today? Yes?
Why did we choose these equal to 4.2?
Okay, so this is the estimated proportion that favor the candidate, right?
Right.
How much below 54.2% do you have to go before you come up with an estimate that does not favor this candidate?
Less than 50%.
Right.
But why did
What's the difference between 54.2% and 50%? 54.2 and 50%. 4.2%. So it's basically the minimum, or actually the maximum margin of error we could have in order to conclude anything if our point estimate was 54.2%. But you could have chosen something to be even safer, like 3 percentage points, in which case, you know, you start getting some ballooning sample sizes. Other questions? Okay, and there were several people who had questions with the project, so if there are more, then we can do that. Otherwise, have a good weekend.